We propose an algorithm that incorporates multiple repertoire-based priors from simulation for fast online learning in robotics. Among data-efficient online learning in robotics, repertoire-based learning starts by generating a large diverse set of elementary policies in simulation. Then these algorithms learn to pick online the best working policies according to the current situation, such as mechanical damages or an unseen terrain. These policies are then sequenced with a planning algorithm to achieve the given task. For instance, picking elementary policies to walk in different directions to reach a target location. In this work, we generate repertoires for many different situations. For example, a missing leg or on different floor conditions that act as priors for future adaptation. Our main contribution is an algorithm, APROL, to plan the next policy by incorporating these priors and the past observations from the robot when the robot has no information about the current situation. In this experiment, the hexapod has to reach the goal position by avoiding the obstacle. It has a broken leg, and none of the pre-generated repertoires matches the reality. It has to learn to adapt to damage, as well as the reality gap. We can see that using multiple repertoires, APROL allows the robot to quickly adapt to this unseen situation, even when no prior perfectly matches the current situation. By contrast, when the robot uses a single repertoire and no learning, it hits the obstacle and fails to reach the goal. In this task, the arm has to push the objects to various goal locations as quickly as possible. Here, APROL uses several repertoires generated for various objects of different shapes and sizes. Note that none of the repertoires represents the exact object the robot has to push in reality. We can see that using APROL the robots quickly learn to push the objects to the goal locations. We believe APROL can find its application in many different fronts, such as fault tolerance and damage recovery in robotics, adaptation to sudden changes in the environment, transferring controllers learned in simulation to the real robot, and so on.